Welcome everyone to the second of two Bott lectures. Mike Freedman will again be talking, and so let me hand it over to Mike. And
thank you, Cliff.
start.
Yeah, so today I want to talk about a subject which in mathematics and topology is called dynamics. Maybe physicists wouldn't call it dynamics. But before I begin, I just wanted to add a little codicil to yesterday's talk. I got a couple questions which I thought were good by email. And I realized that my presentation yesterday, which was on how under certain situations a Hilbert space tends to break into tensor factors, I expressed this as an empirical finding, but I never tried to answer the question why, and someone asked me why. So I should say that I don't really understand why in detail. It is empirical, but the only thing I can say in retrospect to make it seem less surprising is that if you, in general in mathematics, if you minimize interesting functionals, the solutions, the things that minimize them, often have remarkable internal structure. You know, if you put like a 1 over r to some power potential and try to minimize the potential energy between a bunch of point particles, you know, maybe they'll form a lattice with a, you know, monster group symmetry or something like that. So a lot of structure can be pulled out of minimization processes. And I think that's what we were seeing yesterday. Okay, so the topic today is dynamics. We'll be heading to the Thurston theorem, and trying to gain some control of it, some insight into it. But let me begin with a few vignettes, beautiful things to know about dynamics, whether you're interested in the broader context or not. So the first thing is there's a very interesting action. There's a group action of the group PSL2R on an interval. So first let's start with PSL2R. PSL2R is the orientation hyperbolic isometry. So it acts on the Poincare disk. This wiggly arrows acts. It acts on D2 rel boundary. And since it acts on D2 rel boundary, it also acts just on the boundary. And if I take this group has the fundamental group Z, has the topology of an open solid torus. If I take its universal cover, then that acts on the universal cover of the circle, which is the real line. And I can end-to-point compactify. By adding plus or minus infinity to get it to act on the interval. So if I add the endpoints of the real line, it acts on the interval. But this action actually is in the bi-Lipschitz category. Endpoint compactifying is not does not preserve the analytic quality of this action. It makes it an action by homeomorphisms, but if you look at it carefully, it's actually self-similar homeomorphisms near the end of the interval. So that's why it's by Lipschitz. And it's not an accident that this group action has rather low differentiability, that it's only by Lipschitz. It's a consequence of what's called the Thurston stability theorem. That this action cannot be C1. The Thurston stability theorem is a generalization of the Reeve stability theorem, which says that a foliation, if a compact leaf is simply connected, the nearby leaves must be must look like a product over this compact leaf. So if you have a simply connected compact leaf, the nearby leaves simply sit in the product. And this is proved by analyzing the holonomy of the fundamental group, which is trivial, acting on the normal germs. And Thurston went ahead and analyzed, for example, discrete perfect groups, which from which this generalization follows. So Thurston showed that there are certain perfect groups which also cannot be the fundamental group of compact leaves without the foliation being stable or product near there. But these additional cases are excluded only in C1 and higher differentiability. In lower differentiability, these exotic actions exist and create sort of a bifurcation in the theory of foliations. This bifurcation seems to happen mostly between, well, some cases between C2 and C1 and others between C1 and C2. So we'll have use of this fact. A second sort of introductory fact, which is on the way to Mather-Thurston, is the fact that if you take the homeomorphisms, which are compactly supported in Rn, and just think of it as a discrete group. Don't care about the topology. So sometimes one puts a delta superscript, meaning we're just looking at this as an abstract group. And the statement is that this is a perfect group. And even more strongly, if I take any homeomorphism H in the group, I can actually write it as a commutator of some, I'll call it A and S. So there's a beautiful picture proof for this statement. If I have a compactly supported homeomorphism in Rn, I can think of it as supported in particular in a ball. And I just draw the homeomorphism as this arrow, just make you think that it's the identity outside this ball, that the homeomorphism stirs up what's in the ball. Now, let me define an auxiliary homeomorphism A, which is sort of a geometric series of H. So I take a shrinking family of balls converging to a point, and then in each one, I import a small copy of H, so that's my little arrow. And now I have another compactly supported homeomorphism, which I'm calling A. And consider S being the shift map, where I send one ball over to the next one to the right, limiting to the identity at the accumulation point. So that's the shift map S. And this commutator can be thought of as A times A inverse conjugated by the shift. But if I conjugate A inverse, which is sort of the arrow going in the other direction, if I conjugate it by the shift, it's just A inverse reproduced on this tail. But if I follow A on the whole thing and its inverse on the tail, it cancels the tail and I just get A acting on the head, which was H to begin with. So this extension of H multiplied by its conjugated inverse cancels everything out and we just get H. Now, this is a simple geometric construction of a commutator that gives H. In 1971, Mather has a paper in topology, 2 pages long, in which he does this argument not to a single group element, but to the bar construction. The bar construction is the standard way to produce a simplicial complex whose homology groups are the homology groups of this discrete group. So instead of making this argument on a single H, you make it on the bar complex of all homeomorphisms, then the payoff is not that you find that H is a commutator, but you find basically the general homology class has the form of a commutator. So Mather's argument shows that this group is acyclic. So Mather proved that put it in the classifying space notation, B of the identity component of the homeomorphisms made discrete is homology equivalent to a point. And Thurston got to work on this statement, and eventually the Mather-Thurston theorem came out. The final version was in a paper of Thurston's, a bulletin announcement of Thurston's, but there was some back and forth in creating this statement. So let me state the Mather-Thurston theorem. So now it's promoted to a general manifold. A general manifold X, we'll let X be a smooth manifold of any dimension. And it can have boundary or not boundary. Compact, non-compact, it doesn't matter. If we look at the homeomorphisms of X, no need to take the identity component. And we include it into the homeomorphisms. But here we put the discrete topology on, and here the usual topology. Now this inclusion is a continuous map. And it's conventional to look at what the map induces on classifying spaces, so I'll add the B. And the Mather-Thurston theorem is that this map is a isomorphic, is a acyclic map. And in particular, a cyclic map means it induces an isomorphism on integer homology. If I take the integer homology of these classifying spaces, this map induces isomorphism. Now, the Mather-Thurston theorem is generally stated in a more geometric form, which is essentially this algebraic form passed through the Atiyah-Hertzsprung spectral sequence to convert it into a statement about Bordism instead of homology. And once you pass it into the Bordism form, the geometric statement is that if you have any bundle B with fiber one manifold over another, and again, arbitrary dimensions, that this bundle is cobordant to a bundle with a flat connection. So that means V includes into a one higher dimensional manifold W. And W has another end, which is we'll call V star. And V star has a bundle B star over it with fiber X. And the Bordism has a bundle B bar over it, again with fiber X. So there's a cobordism of bundles such that at this end, at the star end, this is a flat, this is a, well, I'll call it topologically flat bundle. And flat bundle is very close to the idea of a flat connection. Let me define what I mean by a flat bundle in the following picture. So bundle has a base, in this case it's V star, that's a total space. V star, and being flat or having a topologically flat connection simply means that there's a foliation F of codimension, the dimension of the fiber X. So there should be a foliation which is transverse to the fibers. I don't know if that red is easy to see, so I'll write it in white. So there's a foliation, there exists a foliation intersecting the fibers transverse to fibers X. And that's the definition of a flat bundle. It's very much like a flat connection, like in Lie theory, but there's no equivariance to this connection. But it definitely is a flat connection in the sense that if you stand at a fiber and you walk along one of these leaves and come back, as long as it's a small circle that you've walked along, you'll come back to exactly the same point. There's no local holonomy with respect to this flat structure. That's why it's called flat. If you take a very long walk, you could wrap around fundamental group in the base and you could come back like a Mobius band, permuted somewhere else on the fiber, but small loops have no holonomy. So now this theorem, this Thurston theorem, the word topological here is important. Topological can be C0, just meaning this is topologically flat foliation. It can mean, and it's true if we say by Lipschitz. It's basically true in the entire theory of foliations. If you're looking at any paper from the 70s or 80s and you see something in low differentiability, you can always assume it's no worse than by Lipschitz. The only reason they go to low differentiability is to avoid the Thurston stability theorem. And actually by work of Suboy, C1, the Mather-Thurston theorem actually holds for C1. So in other words, given any, so I'll take the manifolds and the bundles all to be in the C infinity category. But the question is, if you can board them to a flat, well, it's not actually necessary to take the structure group of the bundle. I'll take the base to be C infinity manifold. The structure group could be homeo or by Lipschitz. The statement is that you can board to a flat connection. So this should be thought of as a very remarkable statement because most of the bundles we encounter, like the Hopf bundle, they depend on local curvatures. And the idea that they're always would be coborded to a flat situation is sort of an astonishing flexibility in cobordism theory, because in particular, you have to build, this might be simply connected, and now you're building some enormous fundamental group that permits this bundle. I should say that the Mather-Thurston theorem has high differentiability versions, which I'm not going to be talking about today. The high differentiability version requires additional structure on this bundle, the structure, Heffliger structure, and in the presence of the Heffliger structure, then you can get a flat connection at the other end. But it turns out the additional information in the Heffliger structure is redundant at low differentiability, so it can be just stripped from the terminologies. Now, when you can solve a problem canonically, but you need to change the base by cobordism, this is called C principle. It's a sort of a takeoff on the Gromov Osh or H principle. So the H principle refers to subjects like immersion theory, where the objects and morphisms are classified homotopy theoretically. If something sort of a weak structure can be improved to a full structure canonically by a homotopy, then you say that that structure obeys an H principle. A weaker condition is that you come to some obstructions that you can't pass, and to get around these obstructions, you have to change the manifold on which the problem occurs by cobordism. Those are called C for cobordism. Now, the point of my talk today is to show that some range, perhaps all eventually, that's a matter of conjecture, but some range of C principle problems can be solved by the most mild of cobordisms. If you're told that there's some problem, which in this case is flattening a bundle, and you want to know how much you have to change the base to solve it, well, the fact that it's C instead of H says you have to change the base somewhat. You won't be able to use the same base. But I'm going to show you that in many cases, you can solve this problem by what's called a semi-s-cobordism. So that's the mildest possible deformation through a cobordism from a homotopy point of view. So the theorem today will be that much of the Mather-Thurston theorem for Mather-Thurston, it's often, I'll explain this, okay to use semi-s-cobordism. You can get away with changing V by semi-s-cobordism, which I abbreviate SSC. So what is a semi-s-cobordism? Well, a cobordism is a manifold with two ends. So we have W, V on this end, and V star on this end. And we say it's a s-cobordism if the inclusions of the two ends are simple homotopy equivalences. But we say it's a semi-s-cobordism if it's just true for the first end. So the definition of a semi-s-cobordism is that V included into W is a simple homotopy equivalence. But we make no assumption about the other inclusion. So the simplest example of this, where you get the flavor of semi, is suppose you take a contractible manifold, compact contractible manifold K. So for example, the Mazur manifold in dimension 4, let's use M for Mazur. Mazur manifold in dimension 4 has a certain homology 3-sphere on its boundary, non-S3. It's an interesting homology 3-sphere, but this manifold itself is contractible. So if you just cut out a ball from the manifold and look at, or from M and look at what's in between, the Mazur manifold minus the ball is a semi-s-cobordism. The V side, the simple side, is this S3, and the V star side, the side that has complicated fundamental group, is sigma 3. In general, a little homological algebra in the universal cover shows that the inclusion V star into W star is a homology isomorphism with group ring coefficients over the fundamental group of W. But the excitement, the fact that V star is more complicated than V, comes solely from its fundamental group. So it's homologically like W, even with pi1 W coefficients, but we have a long exact sequence that the fundamental group, short exact sequence, sorry, that the fundamental group of V star is the fundamental group of V or W. I'll write it as W, or isomorphic. The kernel is some perfect group. So what I'm going to show you is that the Mather-Thurston theorem can often be dealt with, the C problem and the C principle can often be dealt with by, or in some cases can be dealt with by simply expanding the fundamental group, by extending some perfect group by the desired fundamental group, but creating no other changes in the homotopy type. That this mild expansion allows the solution of the C principle problem. And this is this will be strictly true when V is a 3 manifold. And will require a stabilization, which I'll explain in general. So what I want to do now is sketch the argument that when dimension, this is sort of a warm-up case, that in low dimensions, when the base of the bundle is only three-dimensional, that's really the lowest case where semi-s-cobordisms can be built. In this case, we'll show that the cobordism W of Mather-Thurston can be chosen to be, I'll just say is, or can be made. Here's semi-s-cobordism. Okay, so how does this work? We start with V, and it's boarded by W to some V star over which we have the solution, for which we have a flat connection. And this is four-dimensional. So the natural thing to do is to give it a handle decomposition. And if I'm reading the handles toward V, then they'd have an index 0, 1, 2, 3, and 4. 0 being the local minimum, 4 being local max. 0 and 4 handles can just be canceled by the Morse lemma. 1 handles are a little trickier. It turns out you can find a different cobordism. You can modify W by doing a 1 surgery to trade in a 1 handle for a 2 handle. And similarly, a 3 handle for a 2 handle, dually. But in order to do this trading, you change W by surgery on a circle. And there's an issue whether the bundle extends over surgery on this circle. And that's whether the holonomy around this circle is trivial or not. So just as a special pleading, in order to make the argument work in this low dimension without stabilization, I'm going to assume that the structure group is homeos or by Lipschitz, whatever, homeos of the fiber in the identity component, and that'll mean the holonomy over a circle will be trivial. So this is not, this assumption is for the argument I'm going to show you, which I think is the best introductory argument to the technique, but it's not essential for the statement. What I'm arguing will work even for a general structure group, but it's just necessary to this special proof I'm going to show you. So where we are so far is we've reduced by changing W, by modifying W by 1 surgeries. We've reduced to the case that we only have 2 handles. So let me draw a picture of W with a nice convincing 2 handle. So this picture works by sort of dimensional reduction. We have a 4 manifold here, but I'm drawing it as a 2 manifold. And the 2 handle has a descending 2 cell like this and an ascending 2 cell like that. And what I want you to think about is the reverse surgery. That is, suppose we pull out this ascending 2 handle, then what we'll see is just a product because we've removed the 1 handle that was present. So now it's a product. And we could ask, could the flat connection that we saw over the right end over the 2 circles, could that flat connection be pushed over this 2 handle to what looks like 1 circle now? And the answer is, well, that can be done if and only if the holonomy over this circle, attaching region of the 2 handle, if and only if that holonomy was trivial. If that holonomy is not trivial, we can't make the flat bundle persist while deleting the handle. And of course, we don't expect this to work because we'd be back to the H principle. We wouldn't have built a cobordism at all if we could just pull out these 2 handles. So something has to go wrong with pulling out the 2 handles, and it is this non-extendability of the representation. I should have said that whenever you have a flat connection, associated to as a representation of the base. Representation from pi1, thing that has the flat into the structure group. That's what I'm referring to when I say does or does not extend. So the strategy is to build a special model, which will involve PSL2R twiddle, the thing I began the talk with. We'll build a special model which can kind of pad this handle co-boundary. So let me draw the picture this way. I'm going to build a replacement manifold C, which goes in here. That's a 3 manifold. It's drawn as an arc, but it's a 3 manifold. And it'll be the boundary, it'll be part of the boundary. Something like a ribbon in the picture. So the ribbon is C bar, and its boundaries, its inner boundaries, C. So I'm going to construct this homology. This what's in red here is going to be a homology product, but it's going to have an interesting fundamental group that solves the problem of allowing the extension. Okay, so what are these spaces, these special models that I need to build? So the model, let me say what C bar is first. C bar is made this way. I take a certain Poincare I take a certain homology 3-sphere P and remove an essential arc alpha, gamma and cross with I, where P is the so-called 2, 3, 7 ciphered fibered manifold. So this is a homology 3-sphere. And it's made this way. You take the 2-sphere and with 3 orbifold points of order 2 pi over these numbers, 2, 3, 7. So these are cone points. And then it's a twisted U1 bundle over this orbifold. So it's one of these PSL2R twiddle manifolds. It's a well-known homology sphere. If, by the way, you replace the 7 with a 5, this construction gives you the Poincare homology sphere. And now, what is this removing an arc? Well, sorry, I should have put a minus sign here. I take the Poincare homology sphere and I puncture it. So let me draw a picture. Here's the 3-dimensional homology sphere, 2, 3, 7 sphere. I puncture it. I take an essential arc, gamma in it, and then I cross with I. Well, I'm going to draw the cross with I as kind of an open book, sort of a spun picture. So I'll see the double on the top here. I'll see P bar. I'll see another copy, gamma, gamma bar, P bar. And then P cross, this whole thing P cross I, P minus cross I, will indicate this way. So the I factor is kind of a theta coordinate where between 0 and pi, where I've spun P around to create a homology 4-ball. And this arc, this essential arc, which is essential in the fundamental group, now spins around to give me a knot in connect sum, and that's what C is. C will, by definition, be the top of this picture. It'll be P union P bar minus gamma union gamma bar, which I'll call K sometimes, but not. Now, there's an exact sequence, or not, sorry, not exact sequence, but there's a sequence of groups, which is, I can start with pi1 of C. I can include it into pi1 of P connected some minus P bar. Let me project that onto the first factor. And then this includes into the group that we discussed before, PSL2R twiddle, because that's the kind of cipher manifold this is. And then the point of my opening remark was this acts on any ball. Oh, well, what I showed you is that it acts on an interval. I forgot to show you, I forgot to explain the punchline of this action. Not only does it act on an interval, but it acts on any disk rel boundary. And then by implanting that in a manifold, it acts on any manifold of any dimension. So it acts on any manifold X, particularly this fiber. So let me just clarify that last point. So where I left matters is I had the group PSL2R twiddle acting on an interval, a closed interval. But I can take a closed interval and I can embed it as an arc of a circle. And then I can suspend the circle to get a two-sphere. And when I get this two-sphere, we'll see that the action, see that by embedding this action in the circle, it's the identity on the complementary arc. So when I take the suspension, this action is, there's kind of like a sector in which something interesting is happening. And then there's another big sector on the two-sphere in which the action is just the identity. And I can simply cut out a disk in the identity sector if I want an action on D2, the identity on the boundary. The complementary region would have give such an action. And if I want D3, I just double suspend, and D4 triple suspend, and so on. So I can get an action, I can promote the action on an interval to an action on a disk row boundary. But then if I have a general manifold V, or X, I guess was 20 fiber. If I have a general manifold X, I can always take a ball sitting inside X, and I can consider the action, which is always the identity outside this ball, and inside this ball is whatever action was previously produced. So that explains this action here. The whole point of starting with this interesting Lie group is that it has an action, all but a kind of a boring one, just near a point, but it has an action, non-trivial action on any manifold. So the virtue, the great thing about this model C is that it has this interesting fundamental group that factors through PSL2R, and therefore the fundamental group of this replacement, which is the red arc in the picture here, this replacement for this more simple boundary, which is this simple boundary is just S1 plus D3. This is sort of a homology. The red arc is a homology S1 plus D3 linked to it by cobordism. And this red piece has an interesting fundamental group where this did not. So this can capture the sorry, this should be a D2. So in the white arc, it was this boundary of this D2 that was being cut off by the surgery. But if the boundary of the D2 is essential, then it can be fed into sort of the red arc in the picture instead of the white arc. It can be fed into the model C, where that element can survive. So that's the idea of C, is that C is better than an ordinary solid torus. It's a homology solid torus, but it can keep a representation alive, keep a flat connection alive, so that when I remove the handle, I can maintain, by padding it with this strip, I can maintain the representation with a flat connection. Okay, so that's the idea, but the question is, does it really work? You could ask, isn't this kind of a really weak representation? I mean, this just moves a little bit, moves X around a little bit inside a disk. How can that deal with a general element of holonomy, which is some crazy complicated homeomorphism of X? Well, this is where we use something in dynamics called the simplicity trick. So I showed you already that this group, homeo and also homeo 0, I showed you an argument, at least in the case of Rn, that it's a perfect group. It turns out it's a perfect group for the general fiber X. But it's more than perfect. It's stronger than perfect. It's simple. In fact, it's even what's called uniformly simple, but we don't need that now. So being simple means that the group has no normal subgroups other than itself in the trivial group, or more concretely, if you take any non-trivial element, the normal subgroup it generates is the entire group. This is a very powerful thing, because if we have just one silly non-trivial element of homeomorphisms of X, we have just one element which extends over the homology solid torus C, then we can form everything in its normal closure and extend those as well. So the idea is we have this torus T2, which is the boundary of C. And we have this meridional element on it, if you like, the thing that bounds homologically. But we've discovered that there's some element, this homeomorphism of X, there's some element which you can place on this meridian and then extends over the entire fundamental group of C. But this extension problem isn't really about a particular H. I've sort of been careless. It's really the conjugacy class of H, because in order to distinguish two things in the same conjugacy class, you have to take the fiber and very carefully base point it, and I haven't done that. In other words, I'm claiming it's more or less geometrically obvious that if you have an extension problem that you can solve for one H, you can solve for a conjugate H, because the solution is exactly the same bordism, it's simply reparametrized. So if you can draw it in cross section, this solid torus, homology solid torus, if there's an H that you can solve, you can find the extension problem, then that means you can also find the extension problem for H conjugated by any element gamma. And that we'll call it gamma S. And now if you stick the two solid tori together along an annulus, so it's sort of like boundary connected sum for these homology solid tori, except instead of joining them along disks, you join them along annuli. So it's this entire picture I've drawn here across a circle. Then if you draw along the new meridian, it's a composition of H and the conjugate of H. So what you're doing, and you can get inverses in there as well by reversing meridian and longitude. So basically, if you can solve the extension problem for any non-trivial element, the simplicity trick says you can solve it for all elements. So it's a bootstrap that promotes the seemingly insignificant extension ability of PSL2R to the general case. Okay, so that's the end of the sketch. So what I've done is I've started with a general V. I reduced the cobordism to V star to having only two handles. And then I more or less carved out the two handles, but I had to arrange a padding, which I drew in red here, which allowed the representation, which encodes the flat connection on the right, to extend leftward. Now, of course, this is just a low-dimensional example of where the conclusion of the Mather-Thurston theorem can be sharpened to semi-s-cobordism. And actually, I was working this morning again on trying to do the high-dimensional case fully. It's very close in dimension 4. It's an extremely subtle issue. And I don't know the answer, but what I do know, and it's in the preprint referenced in the abstract, is that if you're willing to stabilize the Mather-Thurston problem, then you can always solve the stabilized problem by a semi-s-cobordism. So maybe that's what I meant by Mather-Thurston off and okay, semi-s-cobordism case. So let me explain this stabilization. Okay, so the problem that we start with is this bundle. And then the solution is some other bundle, but it has this flat structure, spoliation transfers to the fibers. You have to go from here to here. Now, if dimension V is greater than 3, we'll stabilize, which means that we take V and we cross it with some product of spheres. We can take circles, for example. And that X stays alone, and then that automatically crosses total space with the same circles. And this is what we call the stabilized problem. And now we don't ask that the answer, the solution, have a stabilized form. It's just a general form. But we can ask whether the stabilized problem can be solved through a semi-s-cobordism. The answer is yes. So W So this thing exists as a semi-s-cobordism after stabilization. Now, the proof of this is not as simple as the sketch I gave. You can't just go in and look at the handles one at a time. Here you might have noticed the argument I presented was sort of a Mather-Thurston theorem was a black box. I only used the bordism as the answer that their theorem provides and then modified their answer. But as you might suspect, in order to really get the fullest information, you have to find a very geometric proof of Mather-Thurston to dive into and try to modify it to see if the steps in the proof can be made compatible with these more restrictive cobordisms, the semi-s-cobordisms. So fortunately, there's a very nice paper that appeared by Gail Megnez the last year, and it's being published in Geometry and Topology, called Quasi-Complementary Foliations. Which is a generalization of Heffler's structure. And I'll explain that in a moment. And his proof of the Mather-Thurston theorem, which reprises a lot of the great constructions of Thurston from the 70s, can be followed sort of step by step with the help of this model that I described to you, the C and C bar, to improve the outcome. So let me just explain so what are quasi-complementary foliations? Suppose you have a manifold with two foliations on it. So there's a white foliation and a yellow foliation. Then you could ask the question whether the white foliation W is transverse to the yellow foliation Y. And if not, could you say isotope or deform one, cobord or concord one to make them transverse? Well, this is a difficult problem. You usually can't isotope one to be transverse to another, but concording, you may have a hope. And this is actually, this problem of adjusting two foliations to be transverse is actually at the heart of the idea of the Heffliger structure. So let me explain what a Heffliger structure is, which I postponed at the beginning. So the formal way of discussing this, it's a one cocycle in pseudogroup of diffeomorphisms of RQ, where Q is the codimension of the foliation. It's a kind of foliation softened up to be suitable for homotopy theory. So you can pull back Heffliger structures by maps, whereas foliations require a transversality condition to pull back. So very concretely, if you have a manifold, V with a bundle over it, an RQ bundle, which you wonder whether it might actually be the normal bundle of some foliation sitting in V, then a Heffliger structure is a foliation transverse. Sorry, it's a foliation on this. This is a bundle, a Euclidean bundle over V, so it has a 0 section. Let me draw it this way. And a Heffliger structure is a foliation transverse to the fibers. But the question is, so this is transverse to the fibers, but there's a question of whether you can make it transverse to the base as well, V. So is it transverse to the base, or does it through tangent to the base? If you can make it transverse to the base, it induces a foliation on V with the desired normal bundle. So the Heffliger structure can be thought of as a problem of making two foliations transverse. One is the if we take the in this context, if we take our bundle B, actually in this picture V should be B. So we take our bundle B, and then we draw B sitting over B. There's what are called the vertical tangents. Now, these are the tangents to the direction X. And in the Thurston theorem, the appropriate Heffliger structure is the foliation on this vertical tangent bundle, tau, and the problem of whether it can be made transverse to B is the question of whether you can deform to a foliation, deform the Heffliger structure to a foliation. So in Menendez's conception, the the verticals are one foliation, the vertical tangents are one foliation, and the Heffliger structure is the other foliation. And you're trying to arrange tangency within B. So it turns out that in order to do this, you do as much as you can, and you come up to residual pockets, which Thurston called holes, and Menenges calls clefts. The clefts in the foliation are defects, and these have to be sequentially analyzed and removed by cobordism. And the difference between this Menenges's proof and the proof that leads to semi-s-cobordism is removing the clefts. You have to be more careful and remove the clefts by the use of a model which does not damage the topology, but sort of sustains the representation, which dictates the flat connection. Well, in order to remove clefts and insert models, the clefts have to have a certain form of their topology. In particular, it's useful for them to have a circle or at least a sphere factor in the cleft. And when this is not available geometrically, it's automatic in the lowest dimension when the base is three-dimensional. But as the base increases, the clefts may not have these extra circle factors, and that's why they're provided in the stabilization. So that's sort of where stabilization comes in. It's to fit the defects in the foliation, defects between the two foliations, and to make them match with some repertoire of models. If we knew more models, then perhaps we could prove this theorem without the stabilization. And that's actually what I was working on this morning in dimension 4, when V was a 4 manifold. So I think there's more that can be said, but maybe the natural thing is to turn it over to questions and see whether any of those lead in an interesting direction. Thank you.
Thank you, Mike. So anybody, it's open for questions, so you can either write your question in the chat or the Q&A box. And anybody? Mike, I have a question. So what are you thinking with the 4 dimensions? I mean, what is your...
Oh, yeah, so here's the, so if you try to do this, if you try to follow the main path, following Menenges, when V is 3-dimensional, it turns out these clefts are always codimension 2. So let's say that V is dimension P. So the dimension of the cleft is always P minus 2. So when P equals 3, then P minus 2 is 1. And these clefts are circles. And these are actually playing much the role of the circle where the 2 handle attached. So there the cleft is solved. Yeah, so let me just give some perspective. So there's some problem which is circular shape where you can't do some geometry. Okay, and you have to, you're trying to do this geometry, you're making 2 foliations transverse, and there's a place where you're getting stuck, and it's a circle. And the traditional thing, which is what Menenges follows, is you cut out a neighborhood of that circle. So that's S1 cross D2. You throw that out, and then you add back in S1 cross a surface, punctured surface of genus G. So you sort of replace the disk here, if you like, by a high genus surface. And the reason that's done in dynamics is because the problem with this disk was a holonomy extension problem. You had in the bundle, you had something interesting going on over this circle. You can't fill it in the base with a disk without killing that interesting holonomy. But if you replace the disk with a punctured surface, then you can use the fact that the boundary of the punctured surface is now a product of commutators. And everything can be, every holonomy can be represented as a product of commutators because we're in a perfect group. So that's sort of why surgery, why the cobordism first comes in, why this isn't an H principle, but a C principle problem. In order to get your foot in the door and use this fact in dynamics that all these perfect groups are lying around, you need to replace disks with surfaces. And you can see that that blows up the topology quite a lot. Now, if this is now not just the circle being replaced by a disk, but suppose it's a solid torus being replaced by a homology solid torus or some other three manifold, then we can hide, and that's sort of what's going on with the model C that I described. Remember, C was some homology solid torus, but it was built inside with a P connected some P bar, a homology sphere. So C actually has this non-abelian group going around in it. And while it's a rather brutal thing to replace a disk by a high genus surface, it's a much more gentle thing to replace a actual solid torus by homology solid torus, where the high genus of what bounds the meridian is sort of hidden. It doesn't show up in homology. The simplest example of this is a knot complement. If you take the complement of the trefoil knot, you know the longitude of the trefoil knot bounds a punctured torus, not a disk. But that punctured torus is sort of hiding inoffensively inside the trefoil knot complement. It's not showing up in the homology of the complement. So you can sort of say that what we're doing is we're trying to hide the homology of this high genus surface in some larger space where it doesn't affect the homology. And in dimension 4, the problem is not a circle, but a surface of like genus 0, 1, 2, whatever that these clefts could be. And the problem of when the base, instead of being a circle, is a surface, hiding the homology in something homologically is like a neighborhood of that. Well, I see how to do it for spheres and tori, and it's sufficient if I can do it for genus 2. So it's a question of constructing some detailed model.
Well, thank you. Other questions? Okay, well, let's thank Mike for. Oh, wait, there is a question. Here we are.
Yeah.
No, it's just thanking Professor Freedman. So thank you, Mike, for the talk.
Actually, before we sign off, let me just add one detail. If people are interested, I realized I skipped a step in the construction of these, in the construction of the models that I insert. So I mentioned the simplicity trick, that it's necessary to like concatenate many of these C's together along longitudes in order to multiply conjugates of the holonomy. But I forgot to say that that trick alone only gets you homology downstairs. If you want the homology to stay undisturbed in the universal cover to get group ring coefficients, which is this SSC, then there's one further trick, which I won't go into detail, but it has the intriguing header. It's a Bing doubling trick. You know, Bing doubling is a way of replacing the core of a solid torus with two components. This is called the Bing double. And it replaces the core of the solid torus with a two-component link as drawn, each of which by itself is homotopically trivial. And one way of thinking about the Bing doubling trick is it's a way of insulating something from the fundamental group. The whole solid torus feels a fundamental group, but these Bing pairs individually inside do not, since they don't wrap around. And in order to refine the models so that they retain their homological properties in the universal cover, this Bing doubling trick is also used. So if you're interested, that's in the paper.
Well, thank you.
Well, great talk, Mike. Thank you very much.
Yeah, I can tell you, I'm extremely impressed by what Thurston knew in the 1970s. You know, he invented, I mean, he produced this amazing bit of math from like 72 to 76, for which actually got the Fields Medal. And then he sort of dropped it all instantly when he became obsessed with hyperbolic structures on three manifolds. So it's like one career was like going full steam, and it came to a sudden end when he got interested in hyperbolic geometry. Yeah, and it didn't come to an end because he had like run out of things to say. It was just opportunity costs. He couldn't continue writing about that while explaining three manifolds. So it's amazing work, but it has the feeling that it was sort of dropped red hot.
All right, thank you. Okay, well, thanks everyone for coming, and again, thanks, Mike, for
Yeah, thank you guys for setting this up. It's really been fun.
very interesting.
Okay, great. See you then.
Okay, bye guys.
Bye. Hey, say hello to Henry.
I will say hello to Henry for you.
Haven't missed you. Okay, bye.
Bye-bye.